integration by part. So I came up with this name. It's just my description of what this one is about as unfolding rationality of irrational numbers. Right? Some rationality. That's there's no unique about this. So what is how do you usually describe irrational numbers? When you look at decimal digits, right? There is no pattern. That's usually what they say, but that's not the right word. Irrational number, there is no repeating block. That is a very specific pattern, right? So that is description. If you are looking at the digits, and if they're forever, when you're looking at it more and more, if there's no repeating blocks happening, then we call it irrational number. If there is a repeating block, you will discover the repeating block by keep computing it, right? But if there's no repeating blocks, you will never discover the repeating block, and then you cannot conclude there's no repeating block. Maybe the length of this repeating block is something ginormous number that we cannot compute in one generation or two, right? Then you have to mathematically argue that it actually never happens, right? So it's a tricky thing. So it's not a pattern, it's a repeating block. But maybe there is a pattern in there. So I'm introducing a pattern in here. These irrational numbers, for example, a famous irrational number, E, right? Do you know the rough estimate of this one? This one is a 2.71. I don't know the third digit, but it's 2.71. This number is an interesting number, and it shows up a lot in. It's kind of important number. One way to describe why is it important is very technical, what we call the eigenvector, something that is not moving, something fixed under all the actions. So it's an important number in terms of integration, differential equation, all that. So it's a well-known irrational number. If you look at digit, there's no repeating pattern, repeating block, but I will introduce a pattern behind this using the rational number. And if you apply the integration by part over and over, then you will see that. So this is the first time this is slightly different introduction. So I think is a more reasonable from what we were doing. Maybe it was confusing, but later I will introduce a more polished version. From there, you can absorb the theory quickly and more cleaner way. But here is more reasonable. This is something we've been doing, and it is falling out, so that's why I'm introducing like this. So don't think it is too confusing. You will have a better version than this confusing version, but it is more motivational to me. So this is something we've been doing, that you did this one, right? T to the n and e to the t dt is much better than t to the n cosine t, right? Everybody kind of understand this reductive recursive formula, correct? And this is a function or number. This is a function. So we use a notation fn t, for example, instead of x, right? So it's nth function and n plus 1 function. We can calculate recursive formula. And we're going to switch to definite integral. And when you unfold this definite integral, those people spend more time figure it out. Something nice is happening. And it's very similar to this slightly different setup. And then you will see, we'll skip about why they, it's very technical to see, but it's almost the same. T to the n and 1 minus t to the n. In terms of integral, it's just a u substitution. It's pretty straightforward, right? Right, 1 minus t and u substitution, it's very easy substitution. Nothing gets more complicated. And when you look at this 0 and 1 and e to the t, when you unfold this one by doing the recursive formula, something interesting happens, right? It's pretty reasonable. This is something we've been doing. You unfold it, and they realize something interesting happened, and they introduce it. Look at this one, and calculation is not so confusing than just looking at here. It's a definite integral. Is this a number or function? What do you think? It is definitely depending on n, if n is different, but n is not really the functional thing. It's just a little parameter involved in there. So we make it big and make sure. Although it's a simple answer to that, its answer is number, but it keeps confusing students. So I'm doing it here. So that's just this one is integrate what is it? It's 1 minus t raised to n, and exponential function there, right? T going from 0 to 1, is that right? And I need to specify what n is. Let's say n is 10. Then it computes this number, and this is a number, right? E is that 2.71, that number. And if you want to see this as a decimal, and you will put, if it is in the one cell, this percent symbol represents whatever it was just calculated. So if it is in a different cell, maybe what Mathematica remembers the last result, it is not the way in the order is written. But if it is in the one cell like this, is always executed everything in there. So percent symbol always represent a previous line. But don't, if it is a separate, and it might represent something else, because sometimes you hit it, the execution here and there, so that confuses. So I'm going to look at first 100 digits of that, and then it looks something like this. The point is that this is a number, right? If n is 10, this definite integral, I just wrote it down, is a number. But it depends on n. So good notation is that just sequence notation. So here we're going to use I. I is number, n is nth number, right? Make sense? Nth number. So this was a function, nth function, and here's nth number, and we're going to do the recursive formula. This time the recursive formula is between numbers, nth number and n minus first numbers, the relations between that. So let's do the integration by parts. So usually we knock down that power, nth power. So which one were we integrating? E to the t, right? Make sense? E to the t. It's 1 minus t, nth power in e to the t. It's definite integral, so you have to carry the 0 and 1, correct? Good? And what is the negative? Correct? And then we differentiate, correct? 0 to 1, differentiate this guy. So we integrated that one. Now we're differentiating that one. If you differentiate, it's n times, and 1 minus t raised to n minus 1 power. And the negative derivative inside, remember? Derivative inside, when you do the power rule, the negative 1 comes out. So let me color that here. So that becomes actually positive, because integration by part, negative symbols there, the derivative 1 minus t become negative 1, become positive. And this part just go there, and dt. Good? And we recognize this is the same thing, so let's reorganize like this. If you plug in 1, what do you get? 1 minus 1, right? It's 0. And the 0 minus, if you plug in 0 in there, is 1 to the n, always 1. It's 1 times e to the 0 is 1. So it's a negative 1, right? So here's the reason why they set up like this. When you unfold this number, this part is the part that doesn't have an integral. If you set up like this 1 minus t, it avoids e to the 1 show up, e to the first show up. But if you set up like this, you only deal with the e to the 0. You will see that keep coming e to the 0, e to the 0, and you never have to deal with e to the first. E to the first is a difficult number. And when you're unfolding it by setting up like this, they realize that all this number, this shows up in this first time of integration by part, does not have e to the first, but it has e to the 0. E to the 0 is easy. It's just 1, right? And every other number involved in here is something number we know. That was the idea. So anyway, that's that. And I'm going to pull that n out of it. And you see this one is exactly the same thing, 0 to 1. 1 minus t, e to the t. Only thing that is different is exponent n minus 1, right? So would that be okay if I write in minus 1? And it's pulled out. What's left inside is exactly the definition of in minus 1. All right, if you couldn't complete that mathematical exercise, it's a little bit of a problem with when you understand this recursive formula. So I'm going to write this one down. I'm going to repeat that by hand one at a time like this. All right, for example, this one now becomes like the in equals negative 1 plus n times in minus 1, right? If you look at this, our original definition of in, this makes sense when n equals 0. Is that right? N equals 0, n equals 0. What is 1 minus t raised to 0 is 1 as a function. So integral from 0 to 1 makes sense. So I think that smallest index we have to look at is a 0. So I0 subscript 0 makes sense. So we're going to look at this one I. What is the smallest n number we should look at here in this formula? If we allow this index being 0, smallest index 1. So that n equals 1. 1 minus 1 becomes 0. I0. That's a smallest thing that we want to allow here. Actually, it still works, but this is one that they want. Okay, so for example, when you use this formula, you have to start with the first number. Then it tells you what the next number is, and the next number is, and things like this. So usually we state it as this number. When n equals 1, it seems like we want I0, right? If you plug in n equals 0 here, then it is a 0 to 1, e to the t dt. Is that right? What is the antiderivative of the t? E to the t, right? That's the antiderivative. 0 to 1. Here, at the very beginning, you have to deal with e to the first. Minus e to the 0, right? Which is 1. But all the other thing that is involved in here does not have complicated numbers. N, easy number, -1, easy number. So if you unfold it, and something nice happens, and e to the first, the irrational number, is related with some number we know. So it reveals the pattern. So this recursive relation itself is really the pattern of this e to the first. All right, overall, this integration by parts is revealing the secret rationality of irrational number. Okay, so let's just practice one more time what this really means. How do we use it? So we know I0, right? So if you plug in n equals 1, then n equals 1 here, I1 minus -1, n equals 1, you plug in n equals 1, 1 times, n equals 1 here, 1 minus 1, this is I0. Do you see if you plug in n equals 1 to this recursive formula? So it's important to you write down the recursive formula clearly. If something didn't work when you were doing last time, this recursive formula, you probably underestimated this, stating this statement clearly and just go by that rule. Sometimes you can't think everything in your head and juggle everything at the same time. You have to write down a clear statement that is summarizing your lots of thinking, and it is kind of simplifies. It is an effective way of computing all this thing. So it's an important statement. Once you have the statement, just go by that statement. N equals 1, n equals 2, n equals 3, you plug it in there. So n equals 1, does that make sense? Right. What is I0? -1 plus e minus 1. That's what it is, right? So maybe you're going to turn this one into a decimal number. So what is in that? E minus 2, if you simplify this one, correct? All right. So when n equals 2, then you look at this formula again. You plug in n equals 2. N equals 2 there. And formula says there's no n involved in -1, but there is n involved in there. So n is 2. N is 2 is going there. So 2 times. When n is 2, this time becomes 2 minus 1. So I subscript 1. Again, this is a short summary of repetitive use of integration by parts, so that you don't have to do the integration by part. You recognize that there's a clear pattern when you repeat this integration by part. So just focus on that pattern. That pattern is summarized right here. All right? So what is it? -1 plus 2 times, what is I1? We just have calculated I1 in here. We use that. Here's e minus 2. So if you simplify this one, is 2 times e minus -4 times 1 is -5, or something like that. Right? And you repeat this over and again. So you can use computer to keep repeating this process. That was recursive formula, right? So I did that. Redo it again, but this is the definite integral. First time we're doing this recursive formula for definite integral, but idea is the same. Okay? If you keep simplifying, it's difficult to see what the pattern is. The best way to see the pattern is keeping the form exactly where it is, and you can do that. So here is the pattern. This is the part that you really understand. IN. So what I was doing, I started from I0, going to I1, and going to I2 and I3 like that. But I'm going to do the opposite. I'm going to look at this formula and keep unfolding the downwards actually going backwards. So, all right, so let me show you. This is a formula, right? You can apply this formula to any n. Is that right? If it is 100, it is still valid. If this is k, then it's still valid, and so on. So I'm going to write this version down to in minus 1, so that in minus 1 in here is unfolding. So instead of n, I'm going to put n minus 1. There's no n appearing in here, negative 1. Originally there was n in there, right? But that index in the left-hand side is the same index there. So if you're applying n minus 1, this is n minus 1 in here. Does that make sense? If this were 5, and that's 5 right here. If this were 6, that's 6. If this were n minus 1, that must be n minus 1. That's the meaning of this formula, no matter what that index is. So, can somebody volunteer to clarify what the index down here is? Think about the relationship. If it is in, what is the next index in the right-hand side? One less, right? n minus 1. So what should be the right index down there? N minus 2. That is the meaning of this formula. You can just manipulate the formula any way you want, as long as you keep this n appearing that n, one less and all that. So what I'm going to do, now we have this in minus 1 has a new identity here, right? So I can replace that in minus 1 with this one. That will reveal the relationship between in and in minus 2. So here it is. In negative 1 times n is there. Now in minus 1 has this new identity, right? So what is it? Negative 1 plus n minus 1 times in minus 2. So the original formula actually gives you two-step recursive formula. If you have two-step recursive formula, you can't deduce the one-step recursive formula. It's not going to work just using this logic. But if you have one-step formula, you can just extend it to any multi-step in recursive formula. All right? So let's simplify just to get out the pattern here. Negative 1, here's a negative n, and here's a positive n times n minus 1, in minus 2. So we just forget about all the integral. We're just focusing on this guy right here. In equals negative 1 plus n times in minus 1. Simple algebra and logic, that's all we are using to unfold this pattern. All right? Fair enough? So I'd like to make this one as today's exercise number 1. So let me summarize it here. So what is the formula we have right now is that in equals negative 1 minus n plus n times n minus 1 in minus 2. Originally we started with the recursive relation n and n minus 1. Now it became n and n minus 2, right? So I want you to apply this original recursive formula. Use original recursive formula to compute, it's a better word, I think. Compute in minus 2, that appeared here, right? In terms of in minus 3. So what is the gap in between these two indices? N minus 2 and n minus 3. Just one gap, right? Going down by 1. N minus 2 and n minus 3. So that'll work. One index in here, right hand side is one less. Correct? So I want you to apply the star to get in minus 2 is equal to something. In the right hand side, you have only n minus 3 in there. Does it make sense? So apply the star to get a formula just like this one and up here. I just put the check mark here. All right? That's your exercise. All right, did you all get this one? In minus 2, that n shows up in here. You can replace that with n minus 2, and all the n's is replaced with n minus 2. Here, that becomes n minus 2. That becomes n minus 2 minus 1 there. Therefore, it's n minus 3. So we have a statement is in minus 2 is negative 1 times n minus 2 times in minus 3. Does that make sense? Any question? All right, so what are we going to do? We go to this equation in here. That's the end of the exercise. We go to that equation, and you knock this one down one more time, that index in there, in minus 1 minus n times n minus 1. Now this in minus 2 is replaced by this equation there, right? So it goes there, negative 1 plus n minus 2 in minus 3. Good? So if you unfold it here, in equals negative n, negative 1, negative n. Negative makes n times n minus 1, and that makes n times n minus 1 times n minus 2 times in minus 3. All right. To many students, by doing this like this one, they pick up the pattern. I think it's pretty clear because this recursive relation is not so complicated. I think it's pretty clear that it goes like this. And do you see the pattern? Negative 1, negative n times n minus 1, and next one will be negative n times n minus 1 times n minus 2 and things like that. Right? So let me give you one next one in here without really doing this exercise again. Negative 1, n times n minus 1. Next one is n times n minus 1 times n minus 2. Right? And then go n times n minus 1, n minus 2, n minus 3. And what is the index now? N minus 4, right? That's the pattern. You just keep going down like this. You see the pattern? You clearly see the pattern? All this thing negative, and you have one more factor and one more factor, and the last one is a positive. And it has also one more factor in there. Think about the relationship between this indexes here. N minus 3 and n minus 4. Right? One less than that. So let's see if you can go all the way down to I0 in there. See what happened. Negative 1, n minus 1, n minus 1, n minus 2. What is the next number? n minus 1, n minus 2, n minus 3, right? Just keep going like that. And at the very end, there will be something. And the very last one was a positive, right? And this is keep going down all the way down to what number? Index I0. This is a index, and what is the last number you multiplied it here? One higher, right? n minus 4, n minus 3 is one higher index. So it's going to be 1 in there. Is that right? Keep going up. One more. One more is a 2 times, 3 times, all the way up to where? N. Before it must be n minus 1. So what will be this number in here? N times n minus. If you compare these two numbers, you have everything except the last one, right? So n minus 1 all the way 3 times 2, but it does not have 1 in there. And it goes to 1. If you keep unfolding it like this, and this is the formula. And here, all this thing is a number we understand except I0. Do you remember what I0 was? Anybody? I0 was integral of 0 to 1 and e to the t, so it was e minus 1. Okay? So here's the catch. They realize that if you consider really large n here, like 100 or, turns out 200 is enough. It's already very, very good approximation. This in it's not so big. So if you solve this thing for I0, which is where the irrational number hid, everything else is a rational number, right? So next thing they do is you solve this equation for that irrational number, e minus 1. All right? So what is multiplied here? This number. Very inconvenient to write it like this, so they introduce the notation. Anybody know the notation? If you multiply 1, 2, 3, all the way up to n, and this is denoted by n factorial. Have you seen that? Actually, your calculator usually have this. There's exclamation mark. So if you do 5 factorial, that represents 1 times, 2 times, 3 times, 4 times 5. So can you imagine like 20 factorial is a pretty big number? Multiplying all this consecutive integer up to 20. So we're going to denote this number by this, n factorial. So if I divide everything by n factorial, then it is one way to isolate it. But first, we're going to move all that. So here it looks like this. I have n factorial times e minus 1. That is this part, right? All the negative number go to the other side. So it looks like this, in plus 1. I think Yeah, that's right. And this one is a plus n, n minus 1, n minus 1, n minus 2. Go all like that all the way to the last one was this one, right? So here's the n minus 1, n minus 2, all the way down to 3 times 2. If you move all the negative signed one to the other side, it looks like this. Now you divide it by n factorial. E minus 1 is in divided by n factorial. Huge number, right? N factorial. What about this one in here? 1 over n factorial. Is that right? How about this one? Is n divided by n factorial, right? Next one. N times n minus 1 divided by n factorial. Here I'm going to write one more. N times n minus 1 times n minus 2 divided by n factorial. And you keep going like this all the way and n minus 1 all the way down to 3 times 2 divided by n factorial. Did I do all of? Yeah, that's the formula. Okay? So I was saying when n is a pretty big number, this number in here becomes almost a negligible term. Therefore, e minus 1 is very, very close to this remaining part where there's no irrational number. These are all numbers that you can calculate by hand if you have time and money to do this one, right? Yeah, so that irrational number is beginning to unfold. There's a clear pattern in this one. So you can even further simplify. You're going to leave it like this. This is the most mysterious part, shoved it inside and there, it becoming almost negligible. So here's 1 over 1 factorial. There's a nice thing about this n and n factorial. This n factorial go all the way to 1 through n, right? And if you cancel that n, do you see in the denominator you only have n minus 1 factorial remaining? This 1 through n, 1 times 2 times 3 times all the way up to n, that last n cancels, leaving with only up to n minus 1. Does that make sense? So I'm going to do that over here. If I have 5 up there, if I have down there in the 5 factorial, which is 5 times, 4 times, 3 times, 2 times 1. For example, that's what that is, right? And that 5 and 5 cancels, becoming 4 factorial, and numerator is simply 1. So that becomes that. So this is the last 2 term. N and n minus 2 factorial. So if there's a 4 like that, 5 and 4 cancels, becoming only 3 factorial, and numerator is simply 1. So 2 n and n minus 1 is gone. So the largest index number that remaining is n minus 2, and everything else is still there. So it's n minus 2 factorial. Right? And here, the same pattern, all the last largest 3 numbers in the down there factors. So n minus 3 factorial remains. So it became even clearer pattern in there. All the way down, what is it? All the way through n minus 1 up to 2 cancels. Everything is gone except 1. So 1 factorial. So if you solve this thing for e, you have the following. All that plus all the same thing, ditto here, and plus 1 of 1 factorial, plus 1, right? Plus 1. But it is a convention to write this 0 factorial as 1. Okay? So if you accept that convention, 0 factorial is by definition is 1, then we even have a wonderful pattern. 1 divided by 0 factorial plus 1 divided by 1 factorial plus 1 divided by 2 factorial, all the way up to 1 divided by maybe 2015 factorial. And it's, if this is very small, almost e. So it's revealing the pattern. Okay, if you keep adding this one, so let me just claim at this stage and show you using Mathematica and other argument to finish this one off, is like this. You think about this part in here. This is easier to understand. How do you understand 1/3 expanded as a 0.3333 and going like this, right? This is really you have 0.3 and plus 0.03 and plus 0.33003 and plus 0.00003. If you keep adding this one forever, then that number is going to be arbitrarily close to 1/3. That is the meaning of this notation, right? So it's the same thing. If you add 1 over 0 factorial plus 1 over 1 factorial, right? And 1 over 2 factorial, and 1 over 3 factorial, which is 6, 3 times 1 times, like that, 1 over 4 factorial. If you keep adding this like this forever, where is this one going? Is this going to go to infinity because you keep adding this positive number? Not necessarily. Here you keep adding the positive number so it doesn't go to infinity, but it goes to what number? Anybody know where it's going? Not 1. So this is 2 and this is a 6. This is 24, right? 4 factorial. 24 times 5, what is it? 120. Next one is 1 divided by 120. And 1 divided by 120 times 6. And you keep doing that. So in the number line, you just keep going forward like this, right? And there will number. You can arbitrarily close to that number, but will never exceed that number. What is that number? Not 0. You just keep adding numbers. So you're getting larger and larger, but you never go to infinity. There's one letter. What is that number? One letter. E. That's what this calculation is about. If you believe this one is negligible term. If you keep adding and higher, this one becomes very, very small if you believe that, and that is your approximation. So this is a rational number. There's a clear pattern in there. Not only just repeating block, but there is no repeating block of that kind of pattern, but there is a clear pattern to this E unfolded in front of you. It only uses slowly integration by part, which was fairly simple arithmetic and algebra you went through. But if you unfold it, you arrive at here. Okay? So I'm going to show you how this one really compares with actual number. So here, did everything I did make sense kind of overall? Not all the detailed techniques. All right. So here is the way to compute this E to 100 digits. Then I'm going to call that A. So that's this number down to 100 digits. All right? And what I'm going to calculate is this one in here. Let me write down summation notation. All right, this is the same shape, clear pattern. So we can write down the summation. What is the first index? Things are changing. 0 and 1 and 2. That's the index there. So it's a k factorial. Is that right? That's the pattern. 0 and 1. That's the only thing that's changing. And numerator is always 1. Make sense? What is the first index? K equals 0. Right? It's not undefined. It's 0 factorial. This is 1. So what is it supposed to go? All the way to infinity, right? Go all the way to infinity becomes eventually E. But let's just try 100. Let's just go up to 100, right? Then it's not going to be E. It's going to be just approximately E. That's what they're claiming, and I'm about to compare this one here. So you write this one down like this. Once you write it clearly to this sigma notation and have that habit, and let's get used to it, then you can write it in mathematical like this. A sum, that's the sigma notation, and then you write down that formula, 1 divided by k factorial. Okay? That's what your summation. And then you put this 0 to 100 thing like this. K starting from 0, going all the way up to 100. And then it's going to calculate the value. So I'm not going to show that because it's going to keep the exact form, the actual fraction, but what we need is numerical value, right? So I'm going to call that B of this previous one. We just calculate it down to 100. So that's going to be number B. You can see already few digits are all correct. It gets harder to count and how many digits you count and all that. So the best way to compare this one is you subtract these two things, right? And see how many zeros that shows up. What does that mean? All first 100 digits are all the same. That's why you see 0 times 10 to the negative 100, right? So we got all of them right just by doing that, right? So how did they actually come up with that arbitrary precision in Mathematica or in your calculator and all this complicated value? Is actually they figure out all these things. For all the elementary things, sine x and cosine x and e to the x and log x, they found this pattern. So we can just calculate an arbitrary precision. This was all done on paper and pencil. That can be done like this. All right, so if you go down to 50, then you can begin to see little So if I change that to 50, then it's a bit different. You can see 67 digits was all 0. After that, if you subtract it off, they begin to slightly differ. Okay? That's how you interpret this difference. 67 digits were correct. So it's not bad if you have a computer program, if you just go up to 100, you get that much of accuracy. That's a great approximation. All right? So now you witness the irrationality of this irrational number e, right? But we didn't fully understand about this, why this one is a 0, approaching a 0. So that's what I'm about to explain. This is standard analysis I'm about to introduce. So here's the theorem just about this particular one. This in that we are calculating divided by n factorial is approaching 0 as n approaches infinity. Right? You have probably seen a statement like this in the limit calculation and something like that in Calculus 1, but it's probably long forgotten, I know. And this uses squeeze theorem. In, if you think about this, in is a difficult quantity to exactly calculate. So whenever in mathematics there's a difficult quantity, we use squeeze theorem, right? So here is the hard stuff. You're surrounded by easy stuff, and here's another easy stuff. And you realize that this guy is going the same number. Whatever is entrapped in there, they squeeze down to the same number because it's always in between. So therefore, we conclude that whatever is in between that hard thing also approaching the a. That was the squeeze theorem, right? So here's the standard theorem. What is in? In was by definition was 0 to 1 is 1 minus t to the n e to the t and dt. Okay, all you care about is the magnitude of this number, so usually we put an absolute value around it. So we want this one to see what happens, and if you put absolute value around it, sometimes just dealing with the magnitude, and is equal to absolute value of 1 n factorial 0 to 1 and 1 minus t to the n e to the t and dt. Right, all the absolute value. Now I want you to think of it as a Riemann sum. This is multiplied and it's a positive number, so absolute value doesn't do much. So if you put absolute value around this integral part, think about it as a Riemann sum. This also helps you. These in Riemann sum terms could be negative in between, right? So if you add them all up and put in absolute value versus, you put absolute value all the integrands, the sum ends, change every term into positive and add them all up. Which one's the bigger? Think about it. Here's 1 minus 1 and plus 2 absolute value versus 1 plus absolute value negative 1 and absolute value negative. Which one's bigger? Definitely this one's bigger, right? You change each of the term to positive number and add them up, it's bigger. So if you bring that absolute value inside the integral, and you get necessarily get bigger. So not equal. So please have this inequality in your solution. That makes me happy that you understand the relationship between these two things. So you can't just put that inside there like this and claim they're equal. They're not equal. They're actually always, this is less than equal. Does this make sense? Think about this one in here. And also think of it as a Riemann sum. Add them all up, absolute value versus put the absolute value first and add them later. Different order of operation. Okay? So we get that. So that's the right thing to write. And then you realize in between 0 and 1, what is the sign of 1 minus t? Always positive, right? E to the t is always positive. So this guy is always positive anyway. So the absolute value is not necessary. Right? So, but we can look at it here. At this stage, what they try to do is that they replace with maximum value, and it turns out it works nicely. And here is less than or equal to 1 over n factorial, 0 to 1. When you add this all up like a Riemann sum, and between 0 and 1 minus t is this type of graph, y equals 1 minus t, right? Between 0 and 1. Do you agree? That's the graph of y equals 1 minus t. What is the maximum value here? y equals 1. So if you replace this function, n goes outside. If you replace this function 1 minus t with this maximum value y equals 1, then it gets bigger. All the sum end is replaced by largest possibility, of course get bigger, right? Think about it here. 1 and 3 and 2 and 1 is less than, this 3 is the largest one, replaced by 3 and 3 and 3 and 3, and of course you get bigger, right? So you replace that one with the largest possibility as 1. What about e to the t? E to the t looks like this. Y equals e to the t. Between 0 and 1, right? What is the largest value here? Y equals e. So if I replace that part with e, then replacing all the sum ends with the largest possibility, therefore it's even get bigger. So although there's an integral, the whole problem is about integrating this guy. It requires integration by parts, a multiple step, right? And we completely ignore the structure and replace by the simplest, the largest value called maximum, right? So basically what I did is I replaced this entire function with a constant that dominates over that. And it's not equal, but it gets bigger, and it turns out is sufficient enough to squeeze this one down to 0. Squeeze theorem, right? It's not exact calculation. We are replacing this difficult stuff here with an easy stuff and creating this large gap between the actual value and this rough estimate. But it is divided by n factorial, and that's the magic. This n factorial is huge. No matter what's happening in here, this is going to be some constant and divided by it. So what is this number? This is a constant. There's no t in there, right? So e pulled outside, an invisible 1 stays inside, and dt like this. Integral of this one is a t. It's 1 to 0. Do you see that? That is just 1. If antiderivative of this one, 1 is t. So from 1 to 0 is 1 minus 0. So therefore, is e that never changes divided by n factorial. Huge number, right? So this absolute value, we have it here, in divided by n factorial, absolute value, is less than or equal to, is really less than, you have huge, e divided by n factorial, right? And because it's absolute value, will never go below 0. So we accomplish the squeeze setup. This one never goes anywhere. If this guy's squeeze it down to 0, then what's going to happen to this difficult quantity to compute? They're going to go to 0 as well. It's trapped in between. So why is this one going? N factorial going to infinity, obviously, right? Multiply, think about 2000 factorial. You multiply all 1, 2, 3, 2000, this ginormous number. And here's e, never changes, right? So 1 divided by infinity? 0. So therefore, by what theorem? By squeeze theorem, that in divided by n factorial approaches what number? 0. So if you look at this portion of number up to here, and when n is really large, it is very, very close to e. Right? And this number I'm calculating here is not very important. As long as it's a constant, it's going to work. And any continuous function has a maximum value, right? It's called extreme value theorem. Any continuous function in a given closed interval, it always assumes a maximum value. It's going to be always going to be less than or equal to some constant. So it's going to keep the shape in there. So this is really, there's no gap in here. I completely prove that k going from 0 to infinity, this is the final theorem, 1 over k factorial, right? If you keep going to the forever, and this is going to be not approaching, right? It's approaching, but in this notion, if you reach the infinity, then it becomes e. That's the statement. Now, this irrational number e reveals a clear pattern as a sum of a rational number 1 over k factorial. Is that good?